In this video, we're going to continue our discussion on section 5.1, which is talking about polynomials, and specifically in this video, we're going to talk about special polynomials. Okay, so there are some special polynomials that we need to keep in mind for the rest of the discussion of this section. So the first type of special polynomial we'll discuss is called a power function. Okay, and so a power function is a monomial function of the form ax raised to the n power, okay, where a has to be a real number. That means it can be an integer, it can be a decimal, can be a lot of things. X is the variable, and then n is, of course, the exponent on the x. N has to be strictly greater than 0 here, so 8 is not a power function. Okay, so but possible examples are these as follows: 3x, 3x, 5x to the fourth, and negative 8x to the sixth. I could go on for ever and ever, as long as you have a number, a real number out in front, a variable raised to a positive power, a positive integer power, then you have a power function. Okay, and so here are some properties of the power function. So when that power function is even, okay, which means when the degree on that function, it only has one monomial term, so the degree on the monomial term is even, we can say it has certain properties. Okay, so the properties that we can say that it has is that it's overall an even function. So if you remember back a little bit, we've talked about what an even function is. And as a refresher, an even function is such that if you cut the graph down the y-axis, okay, I'm sorry about that. If you cut the graph down the y-axis, you can flip one side of the graph over onto the other, and it will create one picture. And a fancy way of saying that is that it is symmetric around the y-axis. Okay, so any power function that has an exponent that's even, that means it's an even function. The domain of that function is always going to be negative infinity to infinity, and the range of the function will always be from 0 to infinity, so it'll always be positive. Of course, when n is odd, when the exponent is odd, we have a slightly different approach, okay, or different consequences. The function itself is then an odd function. Okay, and the odd function says that the graph is symmetric about the origin, which means if I flipped one side of the graph up and then over, then it would be one picture, and so it would be symmetric. Okay, so I'd have to flip it over the x and the y-axis. Okay, that's an odd function, and the domain of an odd function, or the domain of a power function when the exponent is odd, is negative infinity to infinity, and the range is negative infinity to infinity as well. Okay, so you'll see that it's going down to negative infinity and also up to positive infinity. Okay, so those are the power functions. They will come in handy later on. But let's move on to another concept that's going to be important in this section, and that's identifying real zeros. Okay, so let's talk about what that means. If a polynomial function is factored completely, it's easy to locate the x-intercepts by solving the equation f of x equal to 0 and then using the zero product property. So we've had a lot of practice with this in section 1.2. Okay, in section 1.2, where we solved quadratic equations. Of course, a quadratic is a special type of polynomial, and what we did there was we split up the quadratic not as something like x squared plus 2x plus 1. Okay, we didn't like that form. We could factor that into the form x plus 1 times x plus 1 equals 0. And then we use the fact that if either of these are 0, then the whole thing will be 0. That is called the zero product property. Okay, so that's what they mean by zero product property there. So for each example that we do here, what I want you to do is to list the zeros, and what I mean by zeros is the x-intercept. So the solution to the equation, this f of x equals 0. Okay, so that's why they're called zeros, because we set them equal to 0. Or they're the solutions that get us 0. Okay? And we want to list what we are going to call the multiplicity for each. Okay, so the multiplicity is how many times that root is going to happen. So we've seen this before with quadratic functions. Sometimes we're going to have one answer that's repeated multiple times. That's called the multiplicity. And so we can, in fact, fairly easily list the zeros of a function, of a polynomial, and then from that information, we can find the multiplicity for each function. Okay? So to do that, we're going to, for this example, 5x squared times x plus 2 times x minus 1/2 raised to the 4th power, we're going to use the zero product property, as you and I hopefully should know that we should do. Okay, so I'm going to put parentheses around that first term, and to do the zero product property, all that we have to do is set each of the terms separately, 1, 2, and 3, equal to 0, and solve. Okay, so to do that, we start with 5x squared equals 0. I divide by 5. I get x squared is equal to 0, and I can take the square root. I get x is equal to plus or minus 0, which is really x equals 0. So I know that 1 0 of the polynomial happens at 0, 0. Okay. Second one, we let x plus 2 equal to 0, be equal to 0. We subtract away 2 from either side, and we get that x is equal to negative 2. So a second point on the graph is negative 2, 0. And then the third, we'll go through all of these and then come back for the multiplicity. So the third is x minus 1/2 raised to the 4th power equals 0. Okay, and so to get rid of that power, just as before when we had the squared, we used square root to get rid of it. I have a 4th root here, and so I'm going to use a 4th root to get rid of it. Okay, I did that because it'll get rid of the 4th power, okay, there, and it'll also, any power or any root of 0 is still 0. So what I get is that x minus 1/2 is equal to 0. Still, you could say plus or minus, but it's the same thing. Okay, and thus x equals 1/2. And so the point is 1/2, 0. Now we come back to the multiplicity. Multiplicity means how many times does that solution happen, okay? And it has to do with the degree on each monomial term, okay? So 5x squared means that this happens twice, okay? 5x squared, and so there are 2 solutions there, both identical, so they're the same solution. Then we have negative 2, 0, negative 2, 0, and that, with the degree on that term, is really 1, okay, so x to the 1st power I'll just call it mult, is 1. And then the interesting part, I have x minus 1/2 raised to the 4th power. And so thus the multiplicity is 4. Okay, so that is how we can use, or we can list the zeros of the polynomial and the multiplicity for each. Okay, so here's your turn. I want you to list the zeros of the polynomial that I give here and the multiplicity for each of those solutions.